Folks can hear me? Good. So I'm Alan Halakmi. I'm from AWS, and I'm actually quite excited to share with you what we've been doing in the area of IPv6, particularly with respect to our virtual private cloud, VPC. So just a primer on VPC to start with. And I should note that the first part of the presentation here is really going to look at a lot of IPv4. It's concepts that folks understand, and I want to kind of ground you in the way that we've constructed VPC and in the way in which it operates. And then we'll add v6, and hopefully those two things will make sense. So virtual private cloud gives customers the opportunity to carve out logically an isolated portion of the Amazon infrastructure, and they can use that network to launch resources, typically EC2 instances. So let's talk about what VPC looks like. So we have multiple regions around the globe. In a region, you can launch a VPC. So when you create it in the IPv4 world, you specify a CIDR range for that VPC. And that CIDR range can be a /16 to a /28, and you get to pick the size. You create subnets inside of that VPC. Those allocations are obviously subnets from the CIDR block you define for your VPC. And they're connected by an implicit router. So on each of these subnets, there's a .1 address, and you can use that .1 as a gateway to get to other subnets. To get out of the VPC, we provide gateways. We have an internet gateway. The internet gateway gives you access, obviously, to the internet, and it provides one-to-one stateless NAT, and I'll talk about that in just a moment. We also have something called a virtual private gateway. And the virtual private gateway is the mechanism by which you connect to a VPN, or you can use our private line service called AWS Direct Connect. Each of these subnets is associated with exactly one route table. Now, you can have multiple route tables for your VPC, but subnets can only attach to a single one of them. So in this example, on the bottom left side, I have a default route pointing to the internet gateway. On the bottom right side, I have a route table showing a default route to the virtual private gateway. Note also that there is a route entry in the route table that defines the CIDR block. That is always in the route table. It can't be changed by customers. You can't make a more specific route. And it allows essentially all of the instances that are connected in the VPC via these subnets to appear to be directly connected, certainly from a layer 3 routing perspective. Now, once you have the subnets, you can launch instances, right? So I have an EC2 instance here, 10.0.1.7. It has a network interface attached, and I've given this network interface an elastic IP address, a publicly routable IP address from Amazon's IP pool, 54.2.0.12. Now, in terms of controlling traffic flow, we have network access control lists. These are placed around subnets. The network access control list provides you a stateless mechanism to impose traffic flow constraints. And we also have this notion of security groups. Security groups are stateful firewalls that wrap an instance, but more specifically, they wrap the network interface on the instance. OK, so now that we've defined VPC and its basic components, I'd like to share how VPC actually works under the hood. So we have a data center, and that data center has physical nodes, physical hosts. And we call this the substrate, the EC2 substrate. So customers launch instances, and we place them on these hosts in the substrate. So you can see here, one customer with their blue VPC has launched 10.0.0.2, and we've placed it onto the host 192.168.0.3. That customer can continue to launch new instances in their VPC, and we place that across the infrastructure. And of course, we're multi-tenant. So in addition to the blue VPC, we have the green VPC, which may be a different customer. We have the gray VPC. These things are all sharing the infrastructure, but they're logically isolated. In order to understand what the topology is for a given VPC, we have something called the mapping service. The mapping service is responsible for understanding the relationships between a VPC, an instance IP address, and its location in our substrate infrastructure. So there's the question now in this diagram, if I go back one, how does 10.0.0.2 talk to 10.0.0.3? So this is really a layer 2 question. So in a traditional world, right, physical, we have a node 02, it wants to talk to a node 03. So an ARP request will go out. All Fs in the L2 destination. By the way, I'm likely to get source and destination mixed up at some point. We have layer 3 and layer 2, so if I do like yell bingo or something, let me know and I'll correct myself. So ARP request goes out to the broadcast layer 2. Switch doesn't know it, floods that out. 0.3 sees the ARP request, responds, switch caches, and provides that back over to the 0.2 node. And of course, at this point, that node's going to compose a packet with itself is the L2 source, the destination, what it just learned from the ARP response, and obviously the L3 addresses 02 and 03. Packets delivered. So let's see how that works in Amazon VPC. So the instance at 0.2 is going to make an ARP request. Our hypervisor that's running on that host at 192.168.0.3 is going to intercept that, and it's going to make a request to the mapping service. It's going to say, for the blue VPC, where does 0.3 live in the substrate? The mapping service will reply, providing the substrate IP address, where that instance lives, and its virtual MAC address. And then the hypervisor provides a synthetic ARP response back to the instance. Now the instance is ready to compose the packet. Source and destination addresses look very similar to what we saw in the prior example. And that's wrapped in a header for the VPC blue, which is in turn put in an IP packet and sent across our infrastructure. Now on the receiving end, that host does a check. It asks the mapping service, hey, I've got a packet. It came allegedly from blue at blue VPC 10.0.0.2. Does that actually live on the host at 192.168.0.3? The mapping service will confirm that mapping is correct, and then the hypervisor will pass that into the instance. Now, what if the VPC instances are in separate subnets? How would this look at layer 3? Oh, I should actually make a point. Sorry. The VPCs are isolated. So here you see 10.0.0.4. That's the gray VPC. If it tries to make an ARP for 10.0.0.3, you'll see there's no gray 10.0.0.3 here. The mapping service request is made. There's no gray 0.0.3. There's no response. So again, how would this work at layer 3? So back to the physical world. We have our 0.2 node and our 0.3 node. This time, we're making an ARP request for the default gateway, right, for the router. The ARP process proceeds as we would expect, and the packet is emitted from the 0.2 instance. And of course, the L2 MAC address is the 0.2's MAC. The destination is the router. L3 source is 2, and L3 destination is 1.3. That gets sent to the router. As we know, the MAC addresses get flopped, so L2 source is now the MAC address of the router. The destination is the MAC address of the 1.3 node. L3 address is unaffected. So this works pretty much the same way as L2 from an Amazon VPC perspective. So the node at 0.2 wants to talk to the node at 1.3, makes an ARP for the default gateway, what we call the implicit router. That's intercepted by the hypervisor, sent to the mapping service, and the mapping service understands that Amazon's VPC infrastructure is the implicit router. There isn't a node on the network. So the mapping service replies saying, hey, this is the implicit router, and here's the MAC address for the implicit router on the infrastructure. That ARP response is passed to the 0.2 node, and it's now ready to compose the packet to send across to the router. L2 address is the MAC address. The source address is for the 0.2 node. The destination address is the virtual MAC address that was provided for the implicit router. Now, as the hypervisor intercepts that message to the implicit router, it now needs to actually figure out how to get to the L3 destination, this 1.3. So again, it goes back to the mapping service. I need to get to blue 10.0.1.3. Where is it on the infrastructure? The mapping service responds with the MAC address of the 1.3 node and its location on the substrate infrastructure. Packet is composed in the same way that we described just a moment ago in the physical world. Source MAC is 0.2. Destination MAC address is that of the implicit router. Layer 3 source is 0.2, and in destination, layer 3 is 1.3. We wrap it in a VPC header, put it in an IP packet, send it across. And as we showed previously, the receiving host on the substrate infrastructure is going to do a validation with the mapping service to confirm that the packet should actually be making its way over and that the topology is current. The packet's then passed in to the instance at 1.3. So at this point, you are probably wondering about the scalability of the mapping service and the latencies that it introduces. So the mapping service does have visibility. It is kind of the source of truth on topology relative to the virtual private clouds that are running in the infrastructure. But as a matter of practice, it's cached on all the hosts in the substrate. What ends up happening is that each host on the substrate really only needs to know about the VPC topologies for the instances that reside on the particular host. So in the example on the top left, that server really only needs to know about blue and green VPC topologies, bottom left only gray, and so forth. And so these local cache instances subscribe to the mapping service to get topology updates for the relevant VPCs. So we've described how this works inside the context of Amazon's VPC. Now, of course, we need to answer the question, how do we get out from the VPC? So we talked about 10.0.0.2 and how it would communicate internally within a subnet. We've talked about how it would communicate across a subnet. So now the question is, how do we communicate out an internet gateway, for example? Well, if we start composing the packet in the way that we've been saying it, I've got a source, and let's say the destination is this external IP address. I'm going to wrap it in my VPC blue header, put it in an IP packet, but I can't send this to some place on the substrate, right? This 172 address doesn't exist on the substrate. So the question is, where do I send it? Let's go back to the mapping service. As I mentioned, the mapping service is providing a topology view that's cached on each of these hosts. It also is essentially reflective of the route tables as well. So if I look at the cache that sits on this particular host, you'll see that there's a default route that points to an Anycast address for one of our edge fleets. And the edge fleets are essentially protocol converters between VPC land and non-VPC land. So here I see an Anycast address, 192.168.4.3. It's a fleet of edges that provide our internet gateway. This internet gateway is going to provide a one-to-one stateless NAT for this instance. So as this plays out, 0.2 wants to talk to this 176 address. Hypervisor will intercept, provides a mapping. We saw before that mapping points it to this Anycast address space for our internet gateway fleet. It's wrapped and sent across. When it arrives at the edge system is going to pull off the headers that are specific to Amazon, right? The substrate packet isn't material. The VPC tag header is not applicable. Those get pulled off. We have our elastic IP address so that we can actually get this out onto the internet, right? 10 dots are not going to route. So we're going to convert that to a 54 and send that out. Now, one more topic I just want to mention. It'll be relevant when we talk about IPv6. Many of our customers use what we call private subnets when they create their VPCs. And for Amazon, notionally, the difference between a private subnet and a public subnet is simply whether or not the route table has a route to an internet gateway. So in this diagram on the right side, that subnet's associated with a route table with a default gateway pointing to the IGW, the internet gateway, a default route pointing to the internet gateway. And on the left side, the route table is at the moment unspecified, but it certainly is not pointing to an internet gateway. So it's a private subnet. So what customers typically do is they put a NAT gateway in. This is a managed offering that we have that provides port address translation. We give it a public IP address, an elastic IP address. And then in the private subnet, we update the route table to point the default gateway to that NAT gateway. Update the route table as shown, and now traffic that is sourced in that private subnet will go through the NAT gateway, be natted, padded, get a public IP address, and go out the internet gateway. Okay, so that's a lot about VPC and how it works in kind of under the covers, and also what it looks like in the IPv4 world. So now I want to transition to talking about IPv6 and how we've delivered that on top of VPC. So when the project started, we had a couple of tenets. I'll be talking about these throughout, but I want to take a moment just to highlight them. So first is we wanted really to deliver on the V6 promise of end-to-end connectivity. The second is we wanted to offer this as a dual stack solution, allow customers to control where, when, how IPv6 is used in their VPC infrastructure. And then finally, and this is a very important point, we didn't want to make assumptions about customer intent. So we wanted to preserve customer security at the risk of increasing the actions or the number of steps required for customers to enable V6, because we didn't want to unintentionally put customers into a situation where applications broke or they had security vulnerabilities that became exposed on the basis of V6 just turning on without their knowledge. So we wanted to minimize assumptions about the customer intent. So first point, addressing. Should we use unique local addresses? Well, our answer to that is no. We feel that NPT and NAT in general break this end-to-end connectivity tenet, so we don't provide ULA capability. Now, I mentioned earlier about the notion of private subnets, and customers take solace in the notion of having a set of systems that can communicate to the internet, but things on the internet can't communicate back to them, right? One-way doors for traffic initiation. Well, we solved this with something that we call the egress-only internet gateway, and I'll discuss that a little bit more in a bit. The other notion here that's, I think, important, if you look at the RFCs and certainly some of the implementations in various OSs and stacks, IPv4 is actually preferred both for address selection and source and destination selection over ULA. So if we really want to get behind IPv6, providing ULA actually isn't going to move the ball in many cases. So now we're at globally unique addresses, and now the question is, whose addresses do we use? Well, we use our own. So you can go to this URL. This IP ranges JSON file is a list of all the addresses that Amazon is advertising. We have /24s and /25s from all the major registrars, and so those addresses are what we allocate to our customers inside of their VPC. Now, the VPC's subnets are fixed at /64. I mentioned in the IPv4 world, customers have some flexibility in size. In V6, it is fixed at /64. And the VPC CIDR block is /56. Now, if there are RFC weenies here, they're going to ask us why it's not a /48. Well, there are a variety of reasons. I won't go into all of them, but I'll just note that one of the motivations for /48 has to do with IP fragmentation in the route tables and things of that nature. And so given that customers are going to be using our addresses, we're aggregating, so we don't really have that concern. We're able to provide a /56 and obviously aggregate that before it's announced out onto the internet. Now, the other thing that I'll just mention is that most customers in Amazon do not have more than 256 subnets. In fact, when customers get to infrastructures that are that large, they tend to break out into different accounts within Amazon's infrastructure to provide hard boundaries for isolation. Another address thing that comes up, certainly RFCs cover it. If you're using Windows or if you're using a Mac, you're going to have a private address or a temporary address. We don't support that. And the primary reason is it doesn't make sense. The vast majority of use cases that our customers have, they want to be found, right? So they want to use an IP address that's not going to change over time for reasons of DNS TTLs and things of that nature. Customers want to be found, and so this is not supported. All right, so now that we have our address block, it's going to be globally unique. Now the question is, how will it be assigned? Well, we could use static IP addresses, but it turns out that's like really painful in the cloud, right? So folks have essentially ephemeral infrastructures. They're scaling up, they're scaling down. Autoscaling is really hard when you have static IP addresses. Now, our infrastructure will support it, but it's not a mode that we recommend or that we expect most customers will use. We investigated using stateless address auto-configuration. And there are a couple of challenges for us with that. We talked about the mapping service and having a view of the topology, a topology that's controlled by APIs, where customers can call in to create an instance and, in fact, can specify, if they so choose, an IP address or a subnet prefix, etc. So the notion of having the infrastructure controlled by a modified EUI 64 Slack configuration actually doesn't work well with our control plane. We want the control plane to determine the IP addresses, not kind of the happenstance of a virtual MAC address. And we also need to maintain mechanisms that allow us to communicate control plane changes to instances. And so obviously we end up then with DHCP v6. Not only are we able to communicate control plane changes, but we're able to actually handle this in a way that is scalable. And part of that scale is that our DHCP v6 servers are essentially stateless. Our mapping service, our topology map is known, and so whenever an instance reaches out, it doesn't actually matter to us what they're asking for. We can tell them definitively what the topology says they should have and what they should show. So I'll just take a moment. At AWS, I cover conversations around networking and security, so I do want to just pause to, again, talk about this notion of intentionality. So we've made some decisions about how we've designed the v6 implementation, both in terms of what we do as customers enable it, and decisions that we've made about certain RFCs that we're not fully implementing, and I'll explain why. So first, when customers want to enable v6, they have to take an explicit action. It is not enabled by default. It's actually a very trivial thing to do. You go to the VPC and say, I want a v6 block. We assign a /56. You go to a subnet, you say, I want a v6 block. You tell us what the subnet ID should be, and then we assign the /64. But ultimately, you have to enable it on a per interface basis. Now, that can be cumbersome if you have to actually go around each interface and assign it. But we have the ability for you to tell our infrastructure to auto-assign IPv6 addresses at launch, right? So it happens at the interface level. There are actions customers have to take to enable v6. That ties into the second point here. Link local connectivity is not enabled by default. And what I mean by that is most operating systems that launch on EC2 today have an IPv6 stack. That stack will have a link local address. And if you just launched and these instances were able to communicate with each other over link local addresses, applications might start using them. And in fact, that may present security risks to you. So again, a tenet of not assuming intentions of the customer. While the link local address is obviously existent on your particular instance, we will not enable the passing of traffic between link local addresses unless a customer explicitly assigns an address to that interface from the globally unique address pool of that subnet. So link local addresses become available at the moment that the global address is assigned to the interface. We also don't update the route tables. So if you can imagine somebody that has a default gateway that's pointing at their internet gateway, right? So this subnet can access the internet. If a customer was playing around with v6 and we auto-injected a default route for v6 into the route table, that could be bad for the customer. So the only thing that we add to the route table is the VPC CIDR block, the /56, and that essentially has the effect of allowing the subnets to communicate between one another over IPv6, but we make no additional entries that provide connectivity out of the VPC. Now, a similar thing happens with security groups and network access control lists, right? This is how you control flow. Now, it's interesting. If it's the case that you have a default configuration for your network access control list, for example, by default, the network access control list says traffic that originates within the VPC can go out of the VPC, right? Can go through an internet gateway. If you have the default, we will add a v6 route by default as well. If, however, you've modified the default network access control list, as an example, and you've made it more specific, you've customized it in some way, we'll detect that, and we will say the customer has made a conscious choice not to take the defaults, and so we're not going to change the network access control list. The customer will have to take an action. The last 3 points really have to do with RFCs that are out there for protection on the physical network, right? So obviously, we're a software-defined network, so things like RA Guard, Secure Neighbor Discovery, DHCP v6 Shield, these things are really designed to prevent, if you will, bad actors on the infrastructure, are not really relevant to us, right? So if an instance sends out a router advertisement, we're just going to put it in the bit bucket. So there's not a lot for us to do there. So what to do about NAT? Well, I mentioned customers have the warm and fuzzy about this one-way door for traffic that initiates internally, going outbound without the ability for that traffic to be initiated on the external side, i.e. the internet, and come back in. So we created this egress-only internet gateway to solve that conceptual problem for customers. Now, as a matter of practice, the effect of the internet, egress-only internet gateway, EIGW, that can be accomplished with security groups today. But we wanted to kind of have a semantically similar concept that customers could use and have, if you will, some parallelism in the way that they think about their topologies. So the EIGW operates in the way that you expect. All the instances that are running IPv6 in the infrastructure in your VPC, they will have a publicly addressable address, publicly addressable IP. They will send traffic out to the internet. Traffic from the internet, however, cannot source or initiate traffic that's coming back in. The EIGW will drop it. So if we go back to the notion of route tables, if you have a private subnet, you can have a default gateway pointing to an EIGW. So it semantically is similar to the way folks think about NAT gateways. It is providing the security. The privacy piece is a different story. So let's kind of put it together and take a look at how these things connect when we actually look at what happens, again, under the hood at the substrate. So I've got a bunch of systems that have been launched. I've got my blue, green, and gray VPCs. Let's take a look at the layer 2 case. So I want to send a packet to db8::3. Source MAC address is the MAC address of the 2 instance. It's going to make essentially neighborhood solicitation to the for that address on the multicast for the solicited node. That will be intercepted by the hypervisor, consult the mapping service in the way that we described before. Who is blue, ::3, where are they on the substrate? The mapping service will reply with the substrate IP address and the MAC address of that virtual instance. That's passed back in. Packet is composed, sent across, well, tagged, put into an IP address, It is wrapped with a VPC tag, put into an IP, and sent across the infrastructure. On the receiving end, we do the same checks that we did before. Is this mapping between an instance and a substrate host, is that valid? If it's valid, the packet is then passed up to the instance. Okay, let's look at the L3 case. A little bit different than what we saw before. So the first packet out of the gate here is going to have a source MAC address of the 2 instance. It's going to have a destination, L2 destination, of the MAC address for the default, or the implicit router, I should say. The implicit router, that information is known. That's information that came from the router advertisement. So we have our L3 addresses, packets intercepted, mapping service is consulted, the substrate IP is provided, packet is wrapped in the VPC tag, put into an IP packet, and sent across the substrate. When it's received on the other end, the mapping service is consulted again to see if it's a valid mapping for the current state of the topology. The packet is then passed in with the local router link local MAC. The MAC address, obviously, of the :3, and then L3 address is unchanged. So this seems fairly straightforward, but there was a ton of work that was required to do this. And so just a sampling of it, a lot of pieces of the infrastructure, the data plane, and the control plane were affected. We also co-launched, at the time that this was made available to customers generally, we co-launched IPv6 support on AWS Direct Connect. That's our private line service, and our application load balancer. So we have an increasing number of services that are available over IPv6. In the fullness of time, I think you will see all of them be IPv6 enabled. And with that, I welcome questions. Thank you.
Good morning. Interesting to hear what you're doing. You made it look very much as though the infrastructure is and is going to continue being v4, and you're tunneling v6 in v4. Do you anticipate that continuing, or do you anticipate a gradual transition internal?
So the substrate infrastructure is still IPv4 today. We were joking about this outside. It could be Apple talk. It really doesn't matter what it is because it doesn't impact customers. So I guess my answer would be, as the engineering organization sees fit to modify it in order to meet customer needs, then that change will take place. But as far as customers are concerned, they have native IPv6 support.
Okay. Thank you very much for the wonderful talk. So I have a question regarding a little more specifics. Could you spill beans on how do you intercept the packets, and is it like OpenFlow? Do you use OpenFlow controller to cook up the synthetic responses and send back, or how do you do it?
So what you've seen is certainly what I'm able to share just from a knowledge perspective. The real engineers are here today, so happy to answer that question after the talk.
Thanks for the talk. One quick question. You were very explicit about talking about the verification phase on the receipt, but didn't really mention why. I'm assuming maybe race conditions, but I was curious if there's a specific reason.
So I'll share with you a largely correct historical anecdote that explains it. Many moons ago, there was a government agency that was interested in using AWS. And at the time, AWS was essentially a flat infrastructure. So everybody was in the same RFC 1918 space. And this particular US government customer really wanted to use AWS, but in its current form, the CC2 infrastructure that was shared was not usable. And so Amazon did kind of the smart thing and said, well, if you guys know what the government wants, why don't you come build it? And so we hired a bunch of folks from the government, and they built VPC along with folks that we had obviously in Amazon as well. And so part of the reason that validation is there is because the government customer set that we were supporting really wanted to have this notion of packet authorization on both ends.
I think on the egress to the internet, you have some kind of translation, right? Is it done through software, or you have any acceleration in hardware? Would customers face any performance limits if they push a lot of bandwidth out to the internet? Yeah, so the gateways, whether they go out to the internet or to Direct Connect or the EIGW, those are fleets of instances with hardware and software that we control. And so those are microsecond latencies. So customers typically don't see that. And they're horizontally scalable. So customers aren't pegged to a particular device at the edge. That's a fleet that's available to customers.
I know you're caching.
Where's the speaker? Okay.
I know you're caching, but you don't see any performance degradation from going to the mapping service for every single packet?
I can't answer that question, but I can tell you we haven't heard customers complain about packet performance on resolution. If you have an application that would have that issue, I'd love to hear about it.
I got a /56, and I can use, I'm right at the front.
Okay.
All alone in this row. I don't know why.
Yeah.
So I got a /56, and I can get /64s out of that. I have to assign them to an interface. It seems pretty much that I can use one address at a time. Is that correct? Or can I be more creative about my address space as kind of outlined in the previous presentation?
So the way that VPC operates today, you ask Amazon to allocate you a /56. We give you a block. We choose the block. We give that to you. At that point, you can control the subnet ID, if you will. So the bits, whatever that is, 63 and 62. You can control that in defining the subnet ID. And that defines the /64 for that subnet. And that's the extent of control that the customer has on the ID. Obviously, on the bottom 64, you have the ability to request specific IPs and through the API call. So if you want to fill out the bottom 64 in a particular way, you can do that. What most customers do and what we do out of the gate is we just assign it randomly.
Okay, so I have to go through the API to use more addresses than, let's say, that you're giving me through the DHP v6 allocation.
So you can assign multiple addresses to an interface if you so choose.
Okay.
That's absolutely available.
Yeah, I was afraid it was an IPv4 denial of service attack of usage of my IPv6 address space,
No,
but
I
okay.
think you can have quite a few. I was playing with this yesterday. I had 5 addresses on a single interface, so you can have as many as you like
Okay,
within
thanks.
the constraints of that subnet.
Well, you have to show me.
Happy to.
Hi, Alan. Thank you so much for sharing this. This is really inspiring. I have 2 questions. First one is from the architecture and implementation point of view, V4 VPC and V6 VPC is identical or not?
So if you're a customer using VPC, the only difference to you is candidly what the IP looks like. So the concepts that we use in VPC, the VPC itself, the subnets, security groups, how routing works, all of that with the addition of the egress-only internet gateway is essentially the same. So if you want to enable IPv6, it really is just a couple of API calls, and it's enabled on your VPC.
Great, thank you. And the second question is about maybe similar to that question, the mapping service and the mapping service cache. That itself is awesome. And my question is, when do you populate? Is that data-driven, or you pre-populate that cache to the hypervisors?
So the cache is populated from. So the short answer is, as customers make API calls into the control plane, we process it through, and it propagates down to the appropriate nodes, the nodes that the hosts on the substrate that are associated with a particular VPC that's affected. They receive that through essentially pub/sub, but
Great.
that's propagated down.
Thank you so much.
I had a question over here to your right. To your right. Here, oh, sorry. I'll stand here.
The other right, yes.
Hey, thanks. So just a quick question in terms of the RFCs, like the different parts of IPv6 that you're supporting or not supporting. Is there just an accounting somewhere of just, hey, these are the parts of the standard that we support or not support, and then just contact you all if customers want to see more or not?
So we are absolutely driven by customer input. So if there's some RFC that we haven't implemented and there's value to the customer base, we certainly want to hear about it. What I will tell you is the ones that I referenced earlier, as we haven't implemented them, it's really because there's no value, right? So if I put RA guard, for example, the notion of like, hey, there shouldn't be a rogue instance claiming to be a router, it doesn't matter, right? That RA is going to come across and we're going to throw it away. So it's not that in the strictest sense, we haven't, quote, implemented the RFC, but that's because it doesn't make any sense in our context. But if there are capabilities that are of interest, we definitely want to hear customer feedback on that.
Hey, right here. Just a question on the scale of VPCs that can be hosted on a substrate or a server. Is this like a few numbers? Can you comment on that?
Well, it's certainly in terms of IPv6, the limit of scale is 64 to the power of 2, essentially. Actually, it's more than that. It's 56 to the power of 2, or the remainders do the subtraction. But you have that entire address space, right? The bottom segment of that /56. That's the limit. So if you plan to spin up 64 to the power of 2 instances, let us know. We can get you great pricing. But yeah, there's no kind of strict limit in that regards. We have customers that are running thousands of instances.
Cool. Thank you for the presentation. I have a couple of questions. First is, are all the AWS regions now support IPv6? And
Yes.
second, okay, thank you. And second is that are all the address spaces that Amazon allocates are global unique address spaces?
Yes.
Okay. And what are the IPv6 features rollout on your roadmap for the next steps?
So are you asking more generally about feature, or are you asking about VPC
Yes.
in particular?
Both.
So, at the risk of kind of saying what I said earlier, the roadmap for us is completely determined by customer interest. So if there are particular use cases or things that you'd like to see, we want to hear about it. Demand is what drives kind of the roadmap for us. So if you look at kind of our history of how we've rolled out IPv6 to this point, it actually kind of makes a lot of sense from a customer's perspective. So the first launch we had was for our IoT service, right? So not surprisingly, there's a lot of IoT out there. IPv4 is a problem in that space. So that was the first. And then the next set of capabilities that we had were all edge network, right? Our CDN, our DNS service, Route 53. So those types of things. And now we've gradually worked into providing now native IPv6 support in our infrastructure through VPC. So if there are other particular services that are of interest to you, we want to hear about them because it will directly influence the order in which we roll these out.
For the IPv6 support, do you need to use it with a VPC, or can you just launch any instance and have a public IPv6 address attached to that instance? Or do you need to have a VPC?
So the simple answer, everything has like nuance, right? The simple answer is if you're launching in AWS, you really have to have VPC as a construct. So you set up the VPC first. We provide a default VPC, but even in that case, you'd need to enable IPv6 to get the IPv6 addresses. All right, we've exhausted questions.
Are you guys looking to expand v6 support over IPsec tunnels?
The short answer is yes. Timeline is TBD, but the short answer is yes.
Okay, thank you.
So if a bunch of you need IPv6 over VPN tunnels, let me know, because again, it'll help us prioritize the next set of rollouts for v6.
Hi. So on Direct Connect, would I have secondary BGP session with v6 addresses in it? How do I route my IPv6 blocks in and out?
I want to make sure I heard the question.
Direct Connect.
Yep.
When I get IPv6 block assigned, how do I route it out of VPC on Direct Connect?
Sure. So in Direct Connect, you go through the process of setting up the connection and then what we call virtual interface. We provide you the IP addresses for each side of the virtual interface. And then once that comes up, we advertise to you over BGP the prefix that was allocated to the VPC to which it is attached. And then we just
if I
do that
already
exchange.
have v4 session, would I have another VLAN with v6 addresses in it?
So it's dual stack. So there are two sessions. There's a v6 peering session and a v4 peering session.
On same VLAN or different VLAN?
On the same VIF. You can do it on the same virtual interface.
Thank you.
Yep.
Any more questions? Well,
Paul, don't you want to share something? Come on, Paul.
So one of the things that Facebook actually uses Amazon for some stuff, and when we started talking to Alan about coming and talking, I didn't realize that all of these things were enabled, and we went through and we enabled. So Instagram still has some assets on VPC and Amazon. So I asked the team. I was like, it's one of the last things that isn't dual stacked at Facebook. I was like, can you go and just dual stack this little bit of traffic that goes to Amazon? So I thought, they'll just put it on the externally facing and not do anything. Well, the team, as I was talking about earlier, the power of Facebook is you don't have to ask them to do the right thing. They went and did it anyway. So they not only they dual stacked the external side, they dual stacked all of the EC2 instances so that they talk back to Facebook over v6. So we are actually using this today in production, and it's working flawlessly. So anyway, I'd like to thank Alan for his talk, and I believe we're ready for lunch, and we'll be back after lunch. Huh? Yeah, I said I believe we're all ready for lunch, and we'll be back with Microsoft after lunch.